So in the last video, we discussed how the periodic properties of atomic radius and electronegativity have an effect on how equally atoms will share their electrons with one another. So today I want to show you 3 sample molecules and show you how that idea plays out. So the first thing I want to look at is if I have 2 chlorine atoms that are bonded next to each other. Here is the Lewis structure for a Cl2 molecule, okay? They each have 7 electrons, they each need 1 more, so they will share an electron with each other. That helps them obey the octet rule, and this is a very stable molecule this way. Now, the question is, are they going to share these electrons equally? Well, because they are the same atom, or not the same atom, because they are identical atoms, they are going to share, they're each going to pull on the number of available electrons in the bond with the same amount of strength. They're the same atomic radius, they have the same electronegativity, so they are going to pull equally. You can almost picture that as thinking, well, if you had 2 twin boys who were fighting over something, they're both, if the twins are identical, they're the same size, they're the same strength, they would be pulling equally and it would be a pretty even tug of war. Okay, so in this particular case, this bond is a true covalent bond, a purely covalent bond, and the atoms will be shared equally. Now, on the other hand, how about if I look at something like this, where I have a hydrogen and a chlorine that are bonded together in a molecule of hydrochloric acid. So the chlorine had 7 and needs 1 more electron. The hydrogen had 1, needs 1 more electron, so they share the electron between them. But in this case, the chlorine wants the electron a whole lot worse than the hydrogen does. And you can verify this by looking in your book at the periodic table where it lists all of the electronegativity numbers. And you'll see that the number for chlorine is higher than the number for hydrogen. And so because the chlorine wants the electron much more than the hydrogen does, it pulls harder, and so it has possession of that pair more often than the hydrogen has possession of it. Sort of like in the example that I gave you in the other video, the 3-year-old pulls harder on the toy than the 1.5-year-old does, and so the 3-year-old gets the toy more of the time. So here, the shared electron pair is held onto by the chlorine more of the time. Now, what happens when that's true? Well, in ionic bonds, we said that if the electron was completely transferred, then the chlorine would have a -1 charge. If the hydrogen completely lost the electron, it would have a +1 charge. Well, this hasn't been a complete transfer. The chlorine doesn't have it all the time, it only has it part of the time. So what happens here is that the chlorine gets it more of the time, so I use the Greek letter delta with a negative sign by it to show that this has a partially negative charge. It doesn't have the electron all the time, so it's not a -1, but it is like a fractional negative charge, a partial negative charge, and the hydrogen has a partial positive charge with it, okay? Let's take this to, let's look at another example and look at water, and if I draw the dot structure for water, I find that it looks like this. Okay, so I have 2 hydrogens bonded to an oxygen, and again, what happens is that the oxygen has a higher electronegativity, and it is going to pull on these electrons a whole lot more than the hydrogens are going to be able to pull on it. So here, the oxygen is going to have a partial negative charge, while the hydrogens both have a partial positive charge on them. And so if you look at these bottom 2 molecules, it almost looks like I have a negative end and a positive end. Or here, it's like I have a negative side, and then this side would be a positive side. So this particular type of bond up here, where the electrons are shared equally, your author calls that a purely covalent bond because the electrons are being shared equally. Other textbooks will call this a non-polar bond because they are shared equally, okay? On these 2 examples here, these are called polar covalent bonds because the electrons are pulled more one direction than they are the other direction. Okay, so purely covalent bonds and polar covalent bonds. This is an equal sharing, and this one is an unequal sharing.